In this presentation, we'll take a closer look at asteroids, which you now understand are the parent bodies of over 99% of the meteorites found on Earth. We will also learn about the asteroid belt and what it can tell us about the solar system. And interestingly, it will also reveal another course theme. As you will soon come to see, everything that has happened in the solar system from this point forward is Jupiter's fault. We've got several learning goals to address in this presentation, and you'll need to learn some new vocabulary words to address them. You'll learn about resonances and the role they play in the structure of the asteroid belt. But as you will see, they play several interesting roles elsewhere in the solar system too. The major takeaway message is composition versus distance in the solar system. Because the surface composition of objects changes with distance from the Sun, we'll soon have to slightly modify one of our major course themes. We know that the parent bodies of meteorites are asteroids, so I've collected all the clues that were revealed in Lesson 6-1 on this slide. Because the vast majority of meteorites are chondrites, objects with higher than average volatile content, this suggests that the vast majority of asteroids must be small. We measured the ages of the meteorite samples and found them to be all older than about 4 billion years, with carbonaceous chondrites being the oldest at around 4.6 billion years. The parent bodies of carbonaceous chondrites then must be the first solid material to accrete when the solar system was forming. A small percentage of the meteorite samples we have clearly have been modified by heat, suggesting they come from a larger object. The fact that we have found so few chondrites and even fewer stony iron and iron meteorites on Earth suggests that the parent bodies of these objects must be rare in comparison to the bulk of the parent bodies in the asteroid belt. The very first discovered, and the largest surviving asteroid, Ceres, was discovered in 1801. The second, Pallas, the third, Juno, and the fourth, Vesta, were all discovered by 1807. For nearly 50 years, all these objects were classified as planets. But by the 1850s, the increasing number of discoveries forced astronomers to reconsider and introduce a new class of objects, asteroids. If this sounds familiar to the story of Pluto, that's because it is. By 1981, about 10,000 asteroids were known, and 100,000 were known by the year 2000. Today, we've observed and cataloged nearly 800,000 of the largest asteroids, and there are likely many more smaller ones out there waiting to be discovered. New search programs, such as the Large Synoptic Survey Telescope, the LSST, promise to catalog over 5 million objects by the mid-2020s. You can learn more about the LSST and how it will find asteroids by watching the video linked from this module's materials page. Like I've said, the types of meteorites we have collected suggest that the majority of asteroids are small. Turns out this is correct. The 4 largest asteroids represent nearly 50% of the mass of the entire asteroid belt. If we look at the distribution of asteroid sizes, we find that for every asteroid, there are 10 asteroids 1/3 of its size. At 25% of the entire mass of the asteroid belt, the dwarf planet Ceres, an object that is 940 kilometers in diameter, has revealed itself as of late to be particularly interesting. You will investigate it further as you complete this module. How do we discover asteroids? We start by taking a series of images of the same part of the sky a few minutes, hours, or even a few days apart. We then line up the images with a computer program and blink between each. The very distant background stars stay stationary in the image, but the much closer asteroids move against the background stars just as the moon and planets change position amongst the constellations each month. See if you can spot the asteroid in these images. The case shown here was easy, just a single asteroid. But as we build ever larger telescopes in deep images, we can see not one or a few, but thousands of asteroids all at the same time. When that happens, it's not easy to visually connect the moving dots like we did above. This is where advanced computational techniques, including machine learning, have to be brought in. To learn more about the challenges of discovering asteroids, watch the video on LSST that's linked from the materials page. With the exception of Ceres, 940 kilometers in diameter, and Vesta, 530 kilometers, whose images are on the left, asteroids in the asteroid belt look like the ones in the image at the right. Small, heavily cratered, and for lack of a better description, potato-shaped. Ceres and Vesta are closer to spherical, like the terrestrial worlds we have explored so far. The Dawn mission has been investigating these worlds, with lots of new data arriving over the past few years. You can read more about these fascinating objects in the Ceres and Vesta content page under this module. Whether a world is spherical like a planet or potato-shaped, like most asteroids, depends strongly on the size or diameter of the world. There's one magic number you have to keep in mind, and that is 600 kilometers. I marked it with a red line on my sketch. The shape of objects whose diameters are less than 600 kilometers fall into what is called the strength regime, meaning that their shape is solely dictated by the strength of the rocky material they're made out of. Objects in the strength regime, which are the dots given on the left-hand side of the diagram, are all irregular in shape and much like the potato-shaped asteroids on the previous slide. The shape of objects larger than 600 kilometers in diameter is dictated by gravity. These objects lie in the gravity regime and fall to the right of the red line on the sketch. The larger gravity of these objects is able to overcome the strength of the rocks that make up the world and crushes the rock in 3 dimensions, creating a spherical object. As you can see, Ceres at 940 kilometers is clearly in the gravity regime. Vesta, at 530 in diameter, is borderline. Remember from lesson 6-1, we used the light reflected off the surface of an object to uniquely identify it, like your fingerprint uniquely identifies you. Well, we've been able to match the reflectance spectra of most achondrite meteorites, eukaryotes are a part of this, to basically only one body in the asteroid belt, and that is Vesta. Crazy, right? Keep this really surprising fact in mind. I'll get back to it shortly. Not only are asteroids potato-shaped, but they are all heavily cratered, indicating they're quite old. Many are covered in regolith, like the surface of the Moon, and such are lacking in small craters because many have been shaken by impacts and filled in by this material. Many look like the image of asteroid Itokawa at top left. If you're thinking it looks like a poorly assembled mishmash of material, you'd be right. It is. It's barely being held together by its own gravity. Let's investigate this. A curious property of asteroids is that the vast majority rotate on their spin axes very slowly. A few spin faster than a period of about 2 hours, which is slow for a small object. This is well below what is referred to as their rotational instability limit, or the highest rotational speed a solid body could achieve before breaking apart if it were the size of a typical asteroid. So these objects could be spinning much faster, but they're not. What this implies is that most asteroids are not solid objects. They're actually what we call rubble piles. Repeated impacts over the age of the solar system have shattered the once solid objects. So most do not spin fast, and those that did no longer exist because they flew apart. Picture yourself letting go as you spin really fast on one of those merry-go-rounds at the park, and you'll get the basic idea. The asteroids are very small and therefore low gravity, so the rubble pile material is just barely gravitationally bound. A nice example of a rubble pile asteroid is seen in the image of asteroid Itokawa at the top. We now have a lot of information about meteorites and their connection to asteroids. The one question we now have to answer is, where did the asteroid belt come from? The first and obvious choice for an answer is that the asteroid belt resulted from the breakup of a larger planet-sized object, as is shown in the GIF that most Star Wars fans will recognize at the top. As fun as that scenario is to imagine, it's still not the correct answer. The asteroid belt is not the result of the disruption of a single object. We know this because we have found carbonaceous chondrite meteorites. Recall that these meteorites and their primitive brethren, the ordinary chondrites, could never have been part of a larger differentiated body. Also, recall one of the major constraints from the Earth-Moon origin discussion in Lesson 2. We knew the Earth and Moon were created out of the same mix of materials because their oxygen isotope ratios were identical. If we look at the oxygen isotopes found in different meteorite classes, as given by the colored ellipses on the figure, we see that none of the meteorite classes have the same ratio of oxygen isotopes. Their chemical fingerprints do not match, which implies that they were never part of the same object or the same mix of material. They all accreted independently of one another. This brings up another question. Why didn't all this available material accrete into a larger object? What prevented the accretion of this material into a single large object like the rest of the planets? Well, this brings our next course theme into play. Everything is Jupiter's fault. This one is absolutely due to the proximity of Jupiter to the asteroid belt. The vast majority of asteroids are constrained to orbit between Mars and Jupiter, and their motions are strongly dictated by that big old planet. Also, there really isn't a lot of material out there. Recall that Ceres itself represents almost 50% of the mass in the asteroid belt. So for the Star Wars fans out there, George Lucas did a lot of things right when depicting asteroids. Their spatial distribution just wasn't one of them. There's a lot of space out there. The average spacing between each asteroid is 10 times larger than the Earth-Moon separation. So even if the asteroid belt did accrete into a single object, it likely wouldn't have happened very fast, and the resulting object wouldn't be any bigger than the Moon. It seems like there should be a lot more material there, so where did it go? Also, the asteroid belt may look like a smooth distribution of material, but there are actually gaps in the distribution of asteroids, as shown in this image. The x-axis gives the distances of the asteroids from the Sun, and the y-axis gives their relative numbers. As you can see, there are big gaps in the asteroid belt, called Kirkwood gaps, where a few asteroids are found. These gaps are results of resonances, found at integer multiples of Jupiter's orbit. Take for example the one labeled 3 to 1. An asteroid found in that gap would orbit the Sun 3 times for every 1 time Jupiter orbits the Sun, hence the 3 to 1 ratio. What that means is that every time the asteroid makes the 3 orbits around the Sun, it's at its smallest distance from Jupiter. Recall what you learned about the gravitational force equation. As the separation of the distance between any two objects decreases, the gravitational force between them increases, as in the given equation here. So in our 3 to 1 example, for every 3 orbits the asteroid makes, Jupiter pushes, or slightly nudges, the asteroid, effectively changing the asteroid's orbit over time, much like you change the orbit of a kid on a swing by pushing them every time they're closest to you. Jupiter does this with any asteroid at any integer multiple of its orbital period. Asteroids at 2 to 1, 3 to 1, 5 to 2, and so on are all moved out of resonance with Jupiter over time. Jupiter will push them into different orbits. Resonances between objects change orbits, effectively removing them from the asteroid belt. What this means is that over time, an asteroid on a nice circular orbit around the Sun can have its orbit significantly modified by Jupiter. Resonances with Jupiter change an otherwise circular orbit to one that is more eccentric. And it doesn't take long. Models show that in about 100,000 years, an asteroid in the middle of the asteroid belt at about 2.8 AU can have its orbit changed enough so that it crosses paths with Earth. Recall also that the mother of all achondrite meteorites was Vesta. This is why all those pieces of Vesta ended up on Earth. Vesta is nearly in resonance with Jupiter, and occasionally pieces of its debris field wander into the 3 to 1 resonance and are pushed out of their orbits and end up crossing paths with Earth. That 10-kilometer object that impacted the Earth 65 million years ago and ended the reign of the dinosaurs, that's also likely a result of resonance interactions with Jupiter. One theory is that 2 large asteroids in the asteroid belt collided over 100 million years ago, creating what is today called the Baptistina family, named after its largest surviving member, asteroid Baptistina. A large piece of the debris from the collision probably wandered into resonance with Jupiter, had its orbit modified by the encounter, and crossed paths with Earth, changing life here in a very profound way. Another interesting property of the asteroid belt is the distribution of asteroids with respect to their compositions. At about 3 AU from the Sun is the midpoint of a distinct dichotomy. Asteroids closest to the Sun than about 3 AU are what we call igneous, or essentially modified by heat. Those farther away from the Sun are primitive and retain the organics and volatile compounds discussed in previous lessons. Closer to the heat of the Sun, we find asteroids devoid of volatiles, with compositions of materials that can withstand the heat, like rock, stony, and iron. This is wonderfully illustrated in the following animation. It shows the orbital motions of over 100,000 asteroids observed by the Sloan Digital Sky Survey, the SDSS, an automated telescope that in the mid-2000s obtained nearly 500,000 observations of asteroids in the solar system, among other things. All asteroid belt asteroids and Trojan asteroids with orbits known to high precision are shown in this animation. The relative sizes of each asteroid are illustrated by the size of the dots in the animation. The average orbital distances of Mercury, Venus, Earth, Mars, and Jupiter are illustrated with rings. The false colors show the compositional diversity of the asteroid belt. The change in composition as one goes from the inner towards the outer belt is clearly visible. Green Vesta family members are seen to orbit the inner belt, fading through the blue C-class asteroids, origins of the carbonaceous chondrite meteorites, in the outer belt. Further out, the two Trojan swarms can be seen trailing and leading Jupiter, which is not shown in the animation. This animation was created by Dr. Alex Parker, a former undergraduate here at the University of Washington. Alex is now a researcher on NASA's New Horizons mission to Pluto. The dividing line in 3AU is a place where we see a dramatic change in composition, not only for objects in the asteroid belt, but for all objects in the solar system. This line at 3AU is called the snow line, or frost line. Either way, this is the distance from the Sun that marks a significant change in composition of worlds. Objects closer to the Sun than 3AU must be made of materials that can withstand the extreme heat of our central star. Those farther from the Sun than this can be composed of more volatile elements. To build planets, satellites, and asteroids, you need solid material. Objects close to the Sun are primarily composed of igneous materials like rock and iron. Objects farther away are also composed of rock and iron, but also are composed of volatiles, yet solid ices. The light elements that make up ices, like hydrogen, helium, carbon, or nitrogen, are the most abundant elements in the universe, but are in the gaseous phase, closer to the Sun, and therefore cannot be used as planetary building blocks. Beyond the snow line, however, these atoms and molecules can condense to form ices, solids that can be used to build worlds, big worlds, in the solar system. And we will start to discuss these big worlds that lie far from the Sun in the next lesson module, so stay tuned to hear about the giant planets, their satellites, and the ring systems.